Hi, I'm Hongnan Chen. Today I'll be presenting our work on predicting object interactions with behavior primitives, an application in stowing task. Stowing, the task of placing objects in cluttered shelves or bins, is a common task in daily life, warehouse, and in manufacturing operations. However, this task is still predominantly carried out by human workers, as stowing is challenging to automate due to the complex multi-object interactions and the long-horizon nature. Modeling this interaction is challenging as it requires the understanding of intrinsic properties of contact and frictions among objects. To illustrate, consider a scenario where we aim to reorganize an object from a table into a cluttered shelf. In this context, a straightforward pick-and-place strategy is ineffective. We need to push the object first to create a graspable pole to pick the object. We then need to reason about multi-object interactions and identify the right place to insert the object to complete the task successfully. While heuristics provide a starting point, they cannot fully address the task due to its dynamic nature. The nature of this task requires determining the characteristics of contact and friction, which is a task that presents considerable difficulties. Consequently, the design of a controller capable of managing such tasks is a meticulous and demanding process. The existing methodology include manually pre-programmed systems exhibit notable limitations. Classical pre-programmed systems struggle with adaptability, unable to efficiently handle variations introduced by different arrangement of different objects on the shelf. In our work, we employ a graph neural network to predict object interactions and optimize behavior primitive parameters. Within our GNN model, each object in the system is represented by respective particles. We define the graph state where graph vertex OT represents an object particle and edges ET denotes the relation between particles. Each vertex OIT consists of the particle position and object attributes, including whether it's dynamic or static, the object it belongs to, its offset to the rigid body center. The control action is represented by the gripper's planned position and the motion of the gripper and the corresponding attributes. The feature of all vertex and edges are processed through encoder multilayer perception, resulting in latent vertex representation denoted as HIO and latent edge representation denoted as HIJE. At each time step, we apply the message function, passing function to the vertex feature and edge feature for several iterations to handle signal propagation. The message passing function, rho E and rho O are multilayer perceptions. Subsequently, we apply an MLP decoder to the vertex feature processor final layer output. The rigid transformation for each individual object is determined by calculating the mean of the decoder outputs corresponding to that object. During the training, our approach begins by sampling a set of random robot action parameters. Following the execution of this action, we collect the ground truth future object state. We take the state and the corresponding action as the input to a graph neural network. The GNN then generates a predicted state of the object based on the robot's action and provided initial state. The loss function using mean squared error compares the ground truth with the GNN's predicted state. Transitioning to control aspect, our system incorporates three parameterized primitive: sweeping, pushing, and transporting, each encapsulating various prehensive and non-prehensive motions. Using trajectory optimization, we sample the parameter within the scale parameter space, utilizing the GNN to predict object movements in responding to that action. We can then select the action that mostly closely align with the desired state. Our system goes a step further by executing these skills in a sequential manner. The skill serves as a higher level of temporal abstractions to facilitate efficient planning. This approach effectively guides our system, enabling it to accomplish stowing tasks with great efficiency. We conducted experiments as illustrated in the top left image and evaluated our method using various objects shown in the bottom left image. Our method was tested with a standard stowing task setup, then with the small objects added to the shelf, followed by object substitution with heavier objects like books, and eventually with non-box-shaped objects such as bottles and slipper rollers on the shelf. We also vary the shelf size. A video here demonstrates how the stowing task can be accomplished using 3 skills: sweeping, pushing, and transporting. Our framework is designed to adaptively accomplish the task using 3 primary skills, proving its efficiency across various objects and scenarios as evidenced here, navigating through different object shapes and sizes effectively. We can also accomplish the task using just 2 skills, pushing and transporting. Even with only 2 skills, our framework can successfully complete the task, which is notably challenging given the cluttered fact of the shelf. To explore our method's adaptability, we extended our experiments to include deformable objects. Interestingly, even though our method was primarily trained using rigid box-shaped objects, it demonstrated admirable generalization capabilities. However, the unique dynamics of deformable objects did present challenges, and the performance was slightly reduced compared to other test cases. However, our method does have its limitations and can encounter failure, particularly when the angle between the object and the cable tip is small, posing difficulties in manipulation. Here is the takeaway summary. We introduced a novel model-based imitation learning framework to learn from minimal demonstrations, which enable robots to acquire complex skills. We create a comprehensive stowing benchmark for long horizon manipulations, which is highly prevalent in various both industrial and household settings. We demonstrate the effectiveness and generalization of our framework across a wide range of real-world experiments in stowing tasks. For additional details, please refer to our paper. Thank you very much for your attention and interest in our work.